Hi everyone, what's up? Welcome back to my tutorial channel. It's Daniel here. Today I'm going to show you how to run a two proportion z-test to the difference between the two proportions. So in this lesson, first I'm going to show you when to use the two proportion z-test, and then I'm going to show you how to perform the critical method and the p-value method. So first, when to use a two proportion z-test. Here, number 2 stands for two symbols. Prop means proportion, and z here stands for the standard normal distribution. So let's look at this situation. Are older, more experienced workers more likely to use a computer at work than younger workers? The General Social Survey took a poll to address this question. They asked 350 employed people aged 25 to 40 whether they used a computer at work, and 259 said they did. They also asked the same question of 500 employed people aged 41 to 65, and 384 of them said they use a computer at work. So here we see that our interest is we want to see whether the older and more experienced workers more likely to use a computer at work than younger workers. So we collect two symbols, and then we are going to compare the proportions of these two symbols in order to make inferences toward the proportion of the two populations. So our interest here is to compare the two population proportion. Here, if I said P1 is the proportion of people aged 25 to 40 who used a computer at work, and P2 is the proportion of people aged 41 to 65 who use a computer at work, we have a test. The null hypothesis says that there is no difference between them. That means P1 is equal to P2. And the alternate one says P1 is less than P2. That means younger workers use less computer at work compared to older and more experienced workers. And we have two testing methods, the critical value method and the p-value method. And of course, we have some assumption. We have to check some assumption before we run the two proportion z-test. In order to run a two proportion z-test, first there are two random symbols that are independent of one another. 2. Each population is at least 20 times as large as the symbol drawn from it. Number 3. The individuals in each symbol are divided into two categories. And number 4. Both symbols contain at least 10 individuals in each category. And before we learn how to run the test, let's get used to some notations. Here I use P1 and P2 for the proportion of category of interest in the two populations. P1 hat and P2 hat are the proportion of category of interest in the two symbols. X1 and X2 are the numbers of individuals in the category of interest in the two symbols. N1 and N2 are the two symbol size. And here we use one more proportion notation, that is P hat. P hat stands for the pooled proportion, and is calculated as X1 plus X2 over N1 plus N2. That means the proportion of the category of interest combined in the two symbols. And the standard error of this proportion is square root of P hat 1 minus P hat times 1 over N1 plus 1 over N2. So these are the notation that we need to know before we run the test. So now let's look at the first method, the critical value method. No matter what methods we use, we have to compute the test statistic. The test statistics here is the z-score of the difference of the two proportions. Z is equal to P1 hat subtract P2 hat in a parenthesis, subtract P1, subtract P2 in a parenthesis. Usually P1 and P2 are not known. However, when we run a test, we assume that the null hypothesis is true. That means P1 is equal to P2. So the difference in the second parenthesis is just 0 because P1 is equal to P2. The standard error here is square root of P hat 1 minus P hat times 1 over n1 plus 1 over n2. So this is the test statistics. And P hat here is the pool proportion. x1 plus x2 over n1 plus n2 is how we calculate it. The critical value method is based on the idea that we should reject the null hypothesis if the value of the test statistics is unusual when we assume that the null hypothesis is true. In this method, we choose a critical value which forms a boundary between values that are considered unusual and values that are not. The region that contains the unusual value is called the critical region. If the value of the test statistics is in the critical region, we reject the null hypothesis. If we reject the null hypothesis after choosing a significant level alpha, we say that the result is statistically significant at alpha level. We also say that null hypothesis is rejected at alpha level. So here let's alpha denote the chosen significance level. The critical value depends on whether the alternate hypothesis is left-tailed, right-tailed, or two-tailed. If we have a left-tailed, the critical value is a negative number. It should be minus z alpha. This is a z-score that separates alpha area to the left and 1 minus alpha area to the right. It should be a negative number. And the critical region is the area to the left of the critical value under the standard normal curve. And here, if the test statistics falls into the critical region, we reject the null hypothesis. That means if z is less than or equal to minus z alpha, we reject the null hypothesis. For the right tail is opposites. We see that the critical value here should be positive, right? As is z alpha. This is the z-score that separates alpha area to the right and 1 minus alpha area to the left. And the critical region is just the area to the right of z alpha. It should be this shaded area. And we reject the null hypothesis if the test statistics falls into the critical region. That means z is greater or equal to z alpha. For the two-tailed, we have two critical values. One is negative and one is positive. The first critical value separates alpha half area to the left and 1 minus alpha half area to the right. And the second critical value is a positive number that separates 1 minus alpha half to the right and alpha half to the left. These two numbers are the negative positive of each other. So if the test statistics falls into either one of the two critical region here, we reject the null hypothesis. That means if z is greater or equal to z alpha half or z is less than or equal to minus z alpha half, we reject the null hypothesis. Performing z-test by the critical value method. So step 1, we state the null and alternate hypothesis. Choose a significant level alpha and find the critical values. Here, the two proportions z-test is actually to the z-test. We just use different test statistics because we use different parameters. However, it's basically to the z-test. And we compute the test statistics assume that the null is true. Determine whether to reject the null hypothesis. If it's left tail, z should be less than or equal to minus z alpha to reject null hypothesis. The right tail, we reject the null hypothesis if z is greater or equal to z alpha, and for the two-tailed, we reject the null hypothesis if z is greater or equal to z alpha half or z is less than or equal to minus z alpha half. Simply, if the test statistic falls into the rejection region or the critical region, we reject the null hypothesis. And the last step, we state the conclusion. Now the p-value method. The p-value method just to measure how strong the evidence against the null hypothesis is, we compute a quantity called the p-value. The p-value is the probability that a number drawn from the distribution of the sample mean would be as extreme as or more extreme than our observed value of sample mean. The more extreme the value, the stronger is the evidence against the null hypothesis. The p-value is the probability, assuming that the null is true, of observing a value of the test statistics that is as extreme as or more extreme than the value actually observed. The smaller the p-value, the stronger the evidence against the null hypothesis. So if we have a left-tailed, the p-value is the area under the standard normal curve to the left of the test statistics z. If we have a right tail, the p-value is the area to the right of the test statistics under the standard normal curve. And if we have a two-tailed, we have the p-value is the sum of the errors in the two tails. So in order to perform the p-value method, first we state the null and the alternate hypothesis. Then we choose a significant level alpha. We compute the test statistics. Then we compute the p-value. If it's left tail, the p-value is probability that z less than little z. Right tail, p-value is probability that z is greater than little z. Two-tailed, p-value is the probability that z is greater than absolute value of z, and probability that z less than minus absolute value of z. And it should be 2 times probability that capital Z is greater than absolute value little z, or 2 times probability that z less than minus absolute value of capital of little z. Step 5. If the p-value is less than alpha, we reject the null hypothesis. Perform a two-proportion z-test. So let's look at this example. So we have learned how to perform the test by two methods, the p-value and the critical value method. So now we are going to apply what we have learned into this example. Example 1, the General Social Survey asked 350 employed people aged 25 to 40 whether they used a computer at work, and 259 said they did. They also asked the same question of 500 employed people aged 41 to 65, and 384 of them said that they used a computer at work. Assume there are two independent random samples from the population of employed people. Can we conclude that the proportion of people who use a computer at work is greater among those aged 41 to 65 than among those aged 25 to 40? Use the alpha level is 0.05. So let's summarize the question. Here, I'm make the group of employed people aged 25 to 40 to be the first population, and the group of all employed people aged 41 to 65 as a second population. So the sample of 350 employed people aged 25 to 40 is the first sample, and the sample of 500 employed people aged 41 to 65 is the second sample. Here x1 is 259 and N1 is 350, because the first symbol, the survey asked 350 employed people age 25 to 40 whether they use a computer at work, and 259 said they did. So 259 is X1 and 350 is N1. Similar, when we look at the second symbol, we have X2 is 384 because 384 of them said yes, and N2 is 500 because we surveyed 500 employed people aged 41 to 65. Here we want to see whether we can conclude that the proportion of people who use a computer at work is greater among those aged 41 to 65, that means the second symbol, compared to the first symbol. So if the second symbol have greater proportion than the first symbol, that means the first symbol have lower proportion compared to the second symbol. So the alternate hypothesis here is P1 is less than P2, not greater, because P1 here is the group of young people, and P2 is the proportion of the group of old people. So this is left tail, not right tail. And then we check the assumption to see whether we can run two proportion z-tests. Here we have two independent random symbols. Here assume these are independent random symbols from population of employed people. And then we see that the population is, of course, should be at least 20 times the symbols. We see that in each symbol, the number in each category is more than 10, right? In the first symbol, 259 is in the first category, and 91 is in the second category. And also in the second symbol, 384 is in the third category, and 116 is in the second category. All of these numbers are greater than 10, right? So all of the assumptions are met, so we can proceed the two proportion z-test. So now let's look at this summary again. We use the formula in the first two slides to find the test statistics. Z is equal to negative 0.94. Just check back the test statistics definition and apply the formula. We have Z is negative 0.94. The critical value method here, we have alpha is 0.05 and this is left tail, so the critical value should be a negative number minus Z 0.05, which is negative 1.64. The critical region is the area to the left of it, and we see that the test statistics Z is greater than negative 1.64. That means it does not fall into the critical region, so we do not reject the null hypothesis. Now the p-value method. The p-value of this test is the error under the standard normal curve to the left of negative 0.94, and it is 0.1736, which is greater than 0.05. So we do not reject the null hypothesis. Remember, the smaller the p-value, the stronger the evidence against the null hypothesis. Here the p-value is large, is greater than 0.05, so we cannot fight against the null hypothesis. So our conclusion is there is insufficient evidence to conclude that the proportion of people who use a computer at work is greater among those aged 41 to 65 and among those aged 25 to 40. So that is it for today. Thanks so much for watching my video. See you on the next video. Bye bye.